All right, this is exam 4, essay 2, and we're going to be talking about the kidneys and how it regulates your blood and urine osmolarity. So we have the kidney, looks like this. Well, actually, this is the nephron. This is from another one. This is the Bowman's capsule. This is the proximal convoluted tubule, descending, ascending. And this is the distal convoluted tubule. This is the collecting duct, and it goes to the calyces and gets excreted as urine. This here is the loop of Henle. And there are paratubular capillaries running everywhere, so we can take stuff from the lumen of the nephron into the paratubular cavities. So with the kidney, with the nephron, there is, so in here, the blood will come in, do its thing, and leave. So this is the afferent arteriole, this is the Bowman's capsule, this is the renal corpuscle, and that's the efferent arteriole. And in this glomerulus, there are certain pressures. There's the blood pressure, which we call hydrostatic pressure. There's the blood colloid osmotic pressure. And there is the renal capsule pressure, which is pushing back on it as well. And so we'll call that HP as well, hydrostatic pressure, but we'll give a C and we'll give a G. And so this is pushing the blood this way. Hydrostatic pressure in the glomerulus is pushing it this way at a rate of 55. BCOP is putting it back in at, or we'll say, no, this is 50. BCOP is pushing it back in at 25, and hydrostatic pressure in the capsule is pushing it back 10, something like that. Anyway, let's say 15. The net is going this way, 10. And so the filtrate is ending up going into the capsule, and that's filtration. It's pretty, not super specific. It is, there are a couple membranes and such inside of the glomerulus and the renal capsule that makes large particles and negatively charged particles not exit, such as proteins. Those are large and negatively charged. Red blood cells are very large. We need things to stay inside of our blood, but it isn't super specific. We get to a process called reabsorption. I'll just put reab. And what this does is it takes stuff from the filtrate and puts it, so from filtrate, goodness gracious, I don't know what I'm doing. It goes from the filtrate back into the blood. That's what reabsorption does. And so it takes the stuff that we filtered, because like I said, filtration is not super specific. It takes stuff from the filtrate and puts it back into the blood. So these are things like sodium, glucose, amino acids, things that our body still needs. Specifically in the distal convoluted tubule is where most of this happens. And we have a couple of different specific proteins for each one of these. This in here is the lumen of the nephron, and this here is our blood. So right here we have, actually we'll say right here first of all, we have the sodium-potassium pump. And so sodium is higher outside, potassium's higher inside. So what sodium wants to do from the lumen, it obviously wants to come in. And so we'll write sodium there. And what it will bring along with it is glucose, amino acids, lactate, just from the energy that sodium made coming in. It also opens the channel for glucose, amino acids, and lactate. And they all have their own specific protein that will do that. So sodium will come in that way. Water will follow sodium, and so there is, water can either go paracellularly like this, or intracellularly through aquaporins. it wants to go where sodium is. And so sodium is higher outside the cell because of this. And sodium is coming in here, so water follows, and then water leaves as well. So we got H2O out here, H2O out here, and it goes into the blood. About 70% of the water and sodium from the lumen is going into the blood. With all this, we have something called solvent drag, which pulls calcium and potassium. It pulls both of these into the blood as well, because they don't want to be stuck here. They want to be where the water is, right? So solvent drag, that's what happens there. Chlorine is a different story. Chlorine will come in through a different way. So sodium comes in, right? We'll say this is sodium. We have hydrogen in here, or not hydrogen. We have basically, yes, hydrogen ions here. And these are acids, and sodium comes in, hydrogen is pushed out. What hydrogen does is it binds to anions. It could be HCO3, it could be whatever, but it binds to an anion. Anion. It's a base most of the time, and it will enter into the cell, and it will be broken down inside the cell. The hydrogen plus the base. Hydrogen will then exit again, and it will continue through this cycle, but the base will exit this way, and because it is negatively charged, it pulls the chlorine into the cell. And there's a leak channel for the chlorine to exit, and life is good. With all these channels, there's something called saturation. Which is basically renal threshold, how much of a substance can get through. And so we have only so many proteins that can continue. And so when these proteins, every one of them is working, there's glucose that cannot enter into the blood. And so it will be, all of those glucose carriers will be saturated, and glucose will be excreted through the urine. And so the renal threshold is the number that glucose can get up to inside of the plasma, in the filtrate, how high it can get before it starts to be excreted through the urine. And so yeah, all the things become saturated, and then you find glucose in the urine, or you can find protein, amino acids inside the blood when this saturation is reached, the renal threshold is reached. Going back to Bowman's capsule, it is important to keep this pressure constant, otherwise things will be messed up and you won't be able to filter blood as freely, or you'll be filtering blood far too much. So what goes on, this afferent arteriole is very close to what is called the distal convoluted tubule, and right here there are cells in the distal convoluted tubule that are called the macula densa, and they're very close to these afferent arterioles, so they're able to tell how high the blood pressure is there, as well as they're very close so they can release certain chemicals to affect the afferent arteriole. When the sodium concentration in the lumen of the distal convoluted tubule is too low, it releases a certain chemical called nitric oxide onto the afferent arteriole, and this afferent arteriole dilates, making a stronger pressure to the glomerulus, increasing the filtration there, and more sodium will be inside of the lumen, making this go back up, which is incredibly important. So that's tubuloglomerular feedback. Another thing that helps glomerular filtration rate is the myogenic response. So when this blood pressure gets too big, and so we're filtering too much, it's a myogenic reflex, and the smooth muscle around the blood vessel starts to constrict, bringing that down. So it's basically, you push me, I push back, and it keeps it regulated. So glomerular filtration rate, which is what we'll talk about now. It's called GFR. glomerular filtration rate, and it goes along with clearance very well. So glomerular filtration rate, it happens, how much, basically we'll talk about clearance, because we have already talked about glomerular filtration rate with the numbers and such. So clearance is how much of a substance is released through the blood. These are a couple of different variables. C of x is clearance of a certain solute. X is a certain solute. U of x is the concentration in the urine. V is the flow rate of how much urine you're producing. And P of x is the plasma concentration. And so P of x is mostly normal. It's going to stay about the same. U of x and V they're susceptible to change. So U of x, urine concentration of x. If you're getting more and more of a certain solute inside of your blood, you're probably going to be filtering it more and more. And so the plasma will be a certain number that is very well regulated. U of x will increase though, because it will be either secreted or filtered more. And so U of x for a certain solute will increase. And if you're drinking more water, then you have to take into account the V as well. And if you have a certain amount of a certain concentration of a certain solute inside of your urine, if it's higher than what it should be, then you know that something's either going wrong with the kidneys or something has been administered too highly, and either carriers are being saturated too much or you just have too much of it inside your blood. A good indicator is creatinine. Creatinine is freely filtered by the blood, by the kidneys. And so creatinine is, let's say, about 125 milligrams per deciliter. That's how much it will be found inside of the urine. And so if a certain substance is above that, let's say 160, then you know that it is also being secreted by the nephron. It is being filtered, and then when it gets to where secretion happens, it is also being secreted, because creatinine is just filtered, it's not secreted. And so you know if a substance gets to 160, it's also being secreted. On the other hand, if something gets to 65, then you can tell that it is being reabsorbed, or there's just not enough of it inside of the blood. So if the creatinine is too low, then you know that something is wrong with the kidneys. If it's too high, something's wrong with the kidneys, something's going on. That is clearance. Now we'll go over renin-angiotensin-aldosterone system. So you are just chilling with your blood and you have angiotensinogen released by the liver. It's just in the blood, it's just floating around. If your blood volume gets too low, if your blood volume gets too low, the kidneys will release renin and convert angiotensinogen to angiotensin 1. And then in the lungs, when the blood makes its way to the lungs, they excrete ACE, which is a converting enzyme, to angiotensin 2. And angiotensin 2 does 4 things. It releases, or it makes the brain release ADH. It makes the kidneys release aldosterone. It vasoconstricts your blood vessels, and it increases your body's want for thirst and sodium, because if you have more sodium, then thirst will follow, or water will follow your sodium inside of your blood. If you get more water, then your blood volume will be increased. Vasoconstriction will help the blood vessels be obviously more constricted, increasing your blood pressure again. And then aldosterone and ADH, this is where it becomes pretty cool. What ADH does inside of the kidneys is it makes aquaporin channels released. And aquaporin channels in the principal cells will take the water inside. The principal cells are in the collecting duct. And it will take water from the lumen, bring it into the blood. And so that's what ADH will do. What aldosterone will do, it will make more sodium be brought into the blood through more, more sodium leak channels in the collecting duct, which will help the sodium potassium pump here, bring more sodium there, bringing more water, and water always follows sodium, so water will follow. It will also yeah, that's all it does. So that is the RAS system. Okay, the last thing we'll talk about is this part here, the loop of Henle. And it's just named after a guy named Henle. What it will do, so the osmolarity of the medulla increases the further you go down. So it starts out at 300 up here, and by the bottom, it's at 1,200. What happens is while you're in the descending part of the nephron, it is only permeable to water, and water will want to go where there's more concentration. And so we're up here, we're at 300. As we start to go down, more water is being brought out of the lumen. And so at the bottom here, inside, the filtrate is very concentrated. It's at 1,200 milliosmoles. On this side of the loop of Henle, salt and chlorine will both be taken out into the interstitial space, because it is becoming more and more diluted as you're going back up. And so we're at 1,200 here. As we start to go up, sodium and chloride want to leave because it's far too concentrated inside as compared to outside. And so it will exit. Another thing is the ascending tubule right here, where sodium and chloride are leaving. They can only be released at, so whatever this is at, it is released at 200 lower than what it's at. And so 1,200, it will be released to, or it'll start releasing when it gets to 1,000. At 800, the inside is at 1,000. That's incorrect. I'll edit that out. Anyway, so that's how it maintains the gradient. With the ADH, when the ADH comes around, it also happens in the loop of Henle where water leaves. The ADH, what happens is it makes even more water leave here. And so the inside becomes a lot more concentrated, you pee less. ADH is called the antidiuretic hormone. Antidiuretic, diuretic means you're peeing. Anti, you stop peeing. So ADH helps us retain more water inside of the blood. The blood. Another thing that ADH does is it helps the collecting duct release more urea. Urea is created by the liver, and it is filtered by the kidneys. And so some of it is still in the blood, but some of it is filtered and some of it is excreted. Some of it's in the interstitial space here, and it's a lot more concentrated down here because of the actions of ADH. So ADH will help the collecting duct help present more urea reabsorbing enzymes to appear inside of the tubular cells. So ADH makes more of those here, and so urea leaves from the collecting tubules. And urea obviously makes the concentrations in the interstitial space a lot higher, and so the lower we are, we're at 1,200. The higher we go, because it is recycled, and it will recycle higher up. With the UTA2 channels, it will be recycled back up there. But it's definitely more concentrated down here, and so it keeps this concentration going. Also down here, more salt and chloride is excreted, keeping the concentration a lot stronger down there. The gradient is higher the lower you go because of those actions from ADH, urea, and water and salt. So when we have a lot more, or when the body is dehydrated, meaning we need more water here, we will release ADH, antidiuretic hormone, which will make more water be reabsorbed, but also it makes more urea be reabsorbed, and the urea will help the gradient, so more water will be reabsorbed even further. And so that's how the kidneys work.